A really warm welcome to everyone. Thanks for coming, and thanks to SAP for having us tonight. So firstly, so a bit about myself. So my name is Stefan. I'm a developer advocate with Zilliz, the company behind the open source vector database Milvus. And as a developer advocate, it's my role to help bridge this divide between users and developers. And so to help you folks get the most out of Milvus, how to overcome your technical hurdles, how to build some really cool stuff with vector databases. So I really love meeting users. I love hearing about what your use cases are, and I'm hoping to meet a lot of you folks after the talks today. So, but before we get coding, I wanted to say a bit about Milvus and yeah, tell you a bit more about like what it's about, why you should use it, and so on. Before we do that, so I've got my QR code on LinkedIn. Really love connecting with you folks. So really welcome sort of connect your LinkedIn, and looking forward, have a chat after the workshop. But let's talk about why Milvus. So I mentioned at the start that 90% of new data in 2025 will be unstructured data. And so that sort of begs the question, how are we going to get all this derived value, and how are we going to sort of apply our applications on top of this? And as I'm sure everyone here knows, the answer is deep learning. And so using deep neural networks to embed these images, video, text, etc., into these vector embeddings. And then it turns out we can use this, well, one of the ways we can use the vectors is we can look at similarity in space as having like a semantic relatedness. So vector search is the new standard. But this sort of necessitates new tools, and especially the vector database. So vector search is the new thing. So, but how are we gonna search through these? How are we gonna store them, index them, if we have say 100 million, a billion, or even a trillion? Well, this is where a vector database comes in, and why we developed Milvus. So Milvus is the most widely adopted vector database, fully open source under the Apache 2 license. And when I say most widely adopted, that's sort of, we can actually quantify that. So if you look at Docker pools, forks, I believe PyPy downloads, as well as the number of stars, it has the biggest open source community around it, which we're very proud of. And it's built by a team of database experts who have a sort of background in distributed systems and have been able to use that knowledge to engineer a specific database that really scales. So high performance, scalable, and highly available. And so here's just sort of like a little diagram of the architecture. So in the fully distributed version, which you can deploy, it will scale to literally tens of billions of vectors with sub 10 millisecond latency. So you'll have a deployment that has a distributed system, looks a bit like that. So you can see there's all sorts of different nodes doing specialized things, passing messages to each other. The separation of storage and compute, that's another really important design principle. Milvus has a really rich functionality. So if you want to do something with your vector database, it's most likely that Milvus has that implemented. So for example, in one of our recent releases, Milvus 2.5, we've introduced a text search or a lexical search. So you can use Milvus to replace your more sort of like standard lexical search database, and just have one database that you can use for both semantic search as well as lexical search. And that's why many industry leaders are using Milvus to solve their hardest problems. So everyone from Salesforce to Bosch, having these really massive deployments, 12 billion, 20 billion, they depend on this every day. And we're really proud to call amongst our users some really big names, Microsoft, NVIDIA, Airbnb, IKEA, just to name a few. So Milvus has a really good scalability, but when you're prototyping, you don't obviously don't want to sort of start off at that 10 billion scale. So Milvus has 3 different deployment types. It has Milvus Lite, which is a version we'll be using in this workshop, which you can load. You can very simply just install a Python package and work in a Jupyter notebook. And then there's Milvus Standalone, which runs via a Docker image. And this is really good for sort of like larger scale prototypes, as well as medium-sized applications in production. And then we have the fully distributed version, which you'd launch via Kubernetes and really scales massively to the tens of billions of vectors. Okay, so because it's open source, Milvus has a fantastic integration across the generative AI technology stack. So having the largest open source community, we've had a lot of integrations contributed. So if there's some other tool that you use in your workflow, most likely there'll be an integration. But let's move on to the demo. So we were very excited when deep research came out. I think it was start of February, and it inspired us. It inspired quite a few people to sort of try and reproduce some of the functionality, some of the results. So that inspired us to develop a research agent of our own. And obviously, it's not like a fully it's nowhere near like the performance capability of OpenAI's deep research, but I think it illustrates a number of very important principles in building agents. So I think it has a really good pedagogical value. So what's important about research agents? So I've just taken some quotes from the blog post release for deep research from OpenAI and tried to sort of like categorize them. And I picked out some common themes. I think one is like this iteration, learning to plan and execute a multi-step trajectory via the reinforcement learning that's happened on the reasoning model. The search, so being trained to for this tool usage, browsing the web, and then these things sort of overlap, and then just like reasoning more generally. So this is an architectural diagram. So before we go into the code, I think it helps to have a higher level picture of what we're building and how it works. So this is like an architectural diagram for Deep Searcher. And you can see it has 2 main parts. The first part is data ingestion. So for this system, we're actually going to get all of our data in advance. Maybe in like another system, you could introduce web search as a tool and fetch additional data as needed. But we're going to ingest and index all of our data in advance, and then store that in our vector database. And once we've done that, then we can serve queries. So imagine that the user comes along, they have a query. In this particular design of a research agent, these are the steps that we follow. We take the query and we break that down into a number of sub-queries to answer that question. Then we look up the vector database. So you can route it to several different sources using the reasoning model. We then look up relevant chunks in the vector database, and then do some reflection. So given that we've retrieved that knowledge from our vector database, and these are the specific sub-queries, we ask the reasoning model, are there any knowledge gaps? So is there anything left to fill in? And so it has to reason over the queries that it's answered so far, as well as the retrieved information. And so this is sort of like where the conditional execution comes in, if you will. So it may say, yes, here are some other questions that we need to answer to fully answer the overall question. Or it might say, no, we've retrieved enough information to write our report, so we'll terminate, we'll exit that loop, and we'll go on to the final report writing stage. And here's like a really quick illustration. So this is, you can check out Deep Searcher on GitHub. The link is in the notebook that I'll provide very shortly. So we may give it a query like, write a report comparing Milvus with other vector databases. So here's the query. And then it breaks that down into a number of subqueries. And then asks, it thinks what it needs to do next. It needs to perform a search on the first subquery question, and then do a vector search in both of the sources. So there's Milvus docs, and what is Milvus? It has two vector DB collections that it's routing to. So then it repeats the same thing. It searches the first subquery, but data from the second source. And then, so now I can move on to the next subquery and essentially just repeat those steps, retrieving all of the relevant information to answer that question. And then it does like a few steps which are not sort of like shown in the output. So it's going to do some re-ranking and say, is this chunk that I've retrieved relevant to the question at hand? So sort of like, yeah, like a re-ranking step on top of the vector database retrieval. Okay, so now we just repeat that for all of the subqueries, and then it does this reflection step. So it reflects, okay, have I answered all the questions that I need to answer to fully write this report? And so in this case, it says no. So here are some new questions for the next iteration. And then it just goes through the same loop a second time, answering these new subqueries. So I'll just sort of skip through these lines. And then once it's done that, then it does another reflection step and says, okay, I believe I've got all the information I need to answer the report. So I'm going to go on to the final step, and I'll write the report. So the conclusion, so Milvus is a compelling choice among vector databases, noteworthy for its high performance, flexible deployment options, yada, yada, yada. So you can see it's retrieved the ground truth. Okay, so let's build it ourselves. And when I say let's build it ourselves, we're going to be implementing the core functionality, but with all of the bells and whistles removed. So it's really just the bare essentials. And I think that could really sort of illustrates the principles at play. And this is just like a really sort of basic design of a research agent. So something that we chose. There's no sort of like set formula. That's something that different teams would make different choices on that. So I want you now to open up this Google Colab notebook. So I've got a bit.ly code as well as let me move my picture. Okay, and a QR code on the screen here. And I just sort of thought, actually, once I move off this slide, how are people going to open up the notebook? So I'll just keep it up here for a few minutes. If you miss out, ask someone at your table to pass along the link. And so once you've done that, open up that Google Colab notebook. So is everyone able to open that up? Okay, awesome. And then, so if you want to follow along, so the first step, the data ingestion is not that interesting. So I've done that in advance. So the data we'll be using is the Milvus website. And basically, I've done a full scrape, the Zilliz website. I've done a full scrape of the Zilliz website. I've then chunked it, turned it from HTML into Markdown, and then embedded those chunks, and then saved that into like a data set file for easy. You can open it using standard tools. So we'll be using the Hugging Face datasets library, for example. Okay, so I think I've given everyone enough time. So now I'm going to actually move across to. Okay, so let me show you the data ingestion at like a very high level. This is just like me hacking something together. So just imagine you sort of, like writing a prototype. So essentially what I did was I just took, I wrote like a spider to scrape the sitemap for Zilliz.com. And then I turned that into a link of URLs. And so that outputs this list of URLs. So these are all the URLs that are given via the sitemap. And then I take those and I actually, so I could have done the step in the spider. I'm just sort of like hacking something together. So as they say, do as I say, not as I do. There's some quick and dirty coding practices here. But I loop over those URLs, I download them, I convert them into HTML, and then I chunk them with LangChain. So break them up recursively into a number of chunks. And so it turns out that, so the Zilliz.com website, so just to give you a sense of the scale, it has 28,500 URLs, and that translates into a bit over 300,000 chunks. So, this is like, not like a massive scale. We'll still be able to use Milvus Lite and do this all in our notebook. Okay, but going over to the main notebook, so this is essentially the Google Colab that you guys are viewing. So if you haven't already, download the Zilliz.com dataset. So that's what I've put together. I've done the chunking and the embedding already. Okay, so with that done, the first step is to read in this dataset file and just like have a look and see like what's going on. So now I'm going to slow down a bit and I'll be going through the steps at a more sort of like leisurely pace so people can follow along. So just to make it, so that I'm not cheating, I'm going to restart my kernel. Okay, so we import our libraries. So PyMilvus is the Python client for Milvus. So it's how you connect to a Milvus database with Python. And we'll be using some other standard tools like, libraries like pandas. So this file, it's in a Parquet dataset file. So the first thing we'll do is we'll read it in with pandas. And then we'll just print off the head. So you can see that this dataset file, as I've set it up, has 3 fields. It has the text, so this is the text of the chunk. It has the source, so this is the URL that chunk came from, as well as the vector embedding. So I just use like a common model from sentence transformers. Again, like not that interesting, I did that at home using my GPU. Okay, and then we can see that as we expected, we've got 312,000 rows. By the way, is this size big enough for everyone or should I make it a bit bigger? Bigger? Okay. Geez, can I do this on the fly? We've got some Visual Studio Code experts in the audience here. Thanks so much, Dan. Righto, so we've opened up our database. We've just had a look at a few entries. We can see like what's actually got inside. Let's now put this into our vector database. So the first step is we have to create this Milvus client object. And this is going to be like our interface to the Milvus vector database on our local system. For the URI, we put in a file name, and that's how PyMilvus knows that we want to use Milvus Lite. If you put in a URL, port number, etc., then you'd be able to connect to like a remote deployment, Milvus standalone running on Docker, or Milvus distributed running via Kubernetes. So we'll open that up. And so now we have to actually, sort of do a bit of housekeeping before we can use our vector database. So I'm going to create a schema for each entity in the vector database. I'm going to create an index. And then I'm actually, so once I've done that, I can create what's called a collection. And a collection is essentially like a table in a relational database. So we tell it what the name is, what the dimension of the embedding is, what the primary field name, what is the vector field name, etc. And then we'll then be able to start putting stuff into this. So let's run that. Okay, so And just for debugging purposes, I printed out that we now have a single collection called default in our vector database, which has the right schema for us to start putting this data in. Okay, so now essentially we just need to iterate over our pandas data frame and insert these into the vector database. I'm doing it in batches of 1,024. I think it actually might be faster if I 10,000, just to make this a bit, I think this will make it faster. Okay, so hopefully this step might take a minute or two, but luckily, as they say, here's one I prepared earlier. So I'm going to load up. I've actually saved my database file from earlier. And if you just want to start from this step, you can go up the top and you can just download that pre-built Milvus Lite database file. Well, actually, let's see how it's going. Yeah, I'm going to kill that, and we'll open up our pre-built vector database. So just going to change this line to the file that I've already created. Oh. Doesn't seem to like that file name, so I'm going to put an underscore in here. And by the way, if anyone wants to stop me at any point, am I going too fast, too slow? Just so we can adjust things. Okay, so this is the database that I cooked up at home, just by running this cell, looping over the rows and inserting them. And just to make sure, I'll run this line here to see. Okay, so what this says is in the collection default, we have 312,000 rows. So I know that there are as many items in the database as I was expecting. Okay, so we've got our vector database. Now we can actually start integrating this into a simple agent. And so we're going to be using, to search this vector database, we have to load up the same embedding model that was used to create those embeddings. And so I know that the one I used was all mini LM, a standard one from the sentence transformers library from Hugging Face. So I'm going to load up that library. Has anyone got any questions at this point? Okay, and so this library, I think it's this model, I think it's like maybe half a gigabyte or something. So there we go, it's loaded. And now just to sort of test things out, I'm going to do a simple search on our database just to check that everything's working nicely. So to do a search, we have to take our search string and then we have to embed it. So I use that model. In this case, the search string will be comparison between Milvus and Weaviate. So that will give us back a query vector. And to do a search, a semantic search, or a similarity search in a vector database with Milvus, we use this Milvus client.search, and then we just pass the collection name, the vector to search for, the fields we want to output, as well as some other items. Okay, so that search finished. Let's see what it gave back. Yeah, so it looks like it's retrieving chunks that are related to Milvus versus Weaviate, and Milvus versus other data sets. So my vibe check is that our vector database is working. Okay, so now let's actually build our agent. And so when I say that we'll be building a simpler version of Deep Searcher, what I mean is I've copied the prompts out of the source code for Deep Searcher. So we'll be using the same prompts as well as more or less the same like sort of agentic workflow. So let's look at the prompts that we've got here. So the first prompt is going to help us take a query or a question and break it down into a number of sub-questions. So the prompt goes a bit like this. To answer this question more comprehensively, please break down the original question, yada, yada, yada. And then when we format it, we put in the original query here. And we give it a few examples. So doing some in-context learning. And instruct it to return the response in Python code as a list. And so, this is just like a system I hacked together quickly. Obviously, like in a production system, you would want to use some sort of library or function for constraining the output so that you know it's going to be well formatted Python code or JSON or whatever. Okay, so that's one of our queries. Then we'll have a re-ranked prompt query. So this one goes like this. Based on the query questions and the retrieved trunk, to determine whether the trunk is helpful in answering the question, you can only return yes or no, yada, yada, yada. So this is going to help filter our chunks. So vector search is much more, I guess, sort of like a rough, inexact type of retrieval. It helps to do some re-ranking or filtering with a large language model or a foundation model on top of that. So we're going to take each of the chunks that we've retrieved from the vector database, and we're going to ask the reasoning model, does this chunk help to answer the question? And so next prompt is reflect. So this one essentially says, are there any gaps in our information? So determine whether additional search queries are needed based on the original query, previous subqueries, and all retrieved document chunks. And then if so, please provide a list of up to 3 search queries for the next iteration. So this is going to be the step that sort of like controls the execution of the loop. So the reasoning model will be able to sort of like keep going in that loop if it thinks there's additional subqueries that need to be answered, or else it will be able to terminate, and then we can go and write the report. And then finally, we have the summary prompt. So this one goes like this. You are an AI content analysis expert, good at summarizing content. Please summarize a specific and detailed answer, yada, yada, yada. So this one, it's going to take all of the information that we've got so far and then ask the reasoning model to synthesize that into a report. So it'll have the original question, it will have all of the sub-questions, as well as all of the filtered related chunks, and use that, synthesize that into a report. So now I'm actually going to run this live. So hopefully this is where things always break for most presenters. Okay, so we'll be using OpenAI's O1 mini model. I've just like hidden my API key here. If you're curious, I think a simple query running report took, it's about like 10 cents with this particular workflow. So yeah, not to worry about like inference blowouts. Okay, so let's just test our OpenAI API, make sure that we've got everything set up nicely. So here's just like a test question, write a 1-sentence bedtime story about a unicorn. So this is the amazing age we're living in. We can automate tasks like this. And let's see what happens. Okay, so under the silver moonlight, a graceful unicorn, yada, yada, yada. So it looks like we can call our API key works, which I've hidden, and we can call that model. So let's move on to the actual loop of the agentic workflow. And the query that we're going to be answering is the same as the one that I showed you in the example output from Deep Searcher, which was write a report comparing Milvus with other vector databases. And so, I'm sort of like prototyping the system. Obviously, like some of this code is not best coding practices. You would want to like break more stuff out into functions. you'd probably want to use like a higher level library to implement this agent if you were doing it yourself. But I'm sort of like doing things sort of without any like additional layers of indirection, so you can really sort of like understand the principles. Okay, so firstly, we take that query and then we turn it into a subquery prompt, which asks the model to break it down into a number of sub-questions. And I've got a bit of a hack here. So these two lines essentially take the output from OpenAI and convert it into a Python list of strings. And I'm sort of like relying on the fact that OpenAI, if you ask this model to give you output in a certain format, it's very likely going to respect that. But obviously in a production system, you would want to use maybe some sort of like a additional feature or library to make sure that your output is well formatted. Okay, so we do that. And then it's broken it down into these 4 sub-questions. So you can see that like these are sort of like orthogonal sub-questions that help us answer the main question. And now this is where the actual sort of like meat of the agent's going to happen. So what we're going to do is we're going to loop through the subqueries. And so while we have subqueries, we'll be performing that loop that I showed you in the diagram. We'll be doing a vector search, retrieving relevant chunks, filtering those chunks, and then asking the model to reflect, does it have all the information that it needs, or does it think there's some gaps in its knowledge? So I'll just go through the cell before I run it. So it's looping over. So while we have subqueries left to do, so we'll take those subqueries, we'll encode all of them in one go, then we'll perform the Milvus search on each of those subqueries. So this is going to return like a list of results. And each of those will have three of the closest matches from the vector database. And if you recall, our vector database contains the entire Zilliz.com website. Okay, so now we've retrieved those results. So what we do is we loop through them and then do some, I think this is just doing some simple sort of like getting them into the format that we want. We're putting the chunks into a dictionary where the key is the ID, the primary key, and that helps to deduplicate. We're probably going to retrieve some similar chunks from our different subqueries. And then we can do the filtering. So I've defined this filter function here. This filter function, it runs a re-rank prompt. And then, so again, like I'm using the fact that this output is going to be, it's going to be in the format that we ask it to, because that's just how O1 Mini works. So my little hack here is like, if there's a Y in the response, then it must be true. And then I apply this filter with a dictionary comprehension. So I just sort of like loop over the chunks, run this filter. If the filter is true, then we keep them. Okay, and then we take the filter chunks, we add them to our dictionary of all the chunks that we've seen so far, as well as we update our set of subqueries that we've seen so far, because at the end, to write the report, we'll need access to all of them. And then we can ask the model to reflect. We can run that reflection prompt. We give it the original query. We give it the questions that have been asked so far. We give it the chunks that have been retrieved and have been judged to be relevant. And then we run O1 Mini model again. So, I think I should have just like broken this out into a function, but I think just like when you're sort of like doing some quick and dirty hacking, this is what things look like. So we run that reflection query, and that query will return either a list of new subqueries if it thinks there's gaps in our knowledge, or just like an empty list if it thinks that that's finished. So that's what this condition here says. So if we have subqueries, then we'll just print them out for debug purposes. Otherwise, we'll print no new subqueries. And because of the condition of the loop, while len subqueries, it will then terminate that loop. So let's run this, and hopefully nothing breaks. Okay, so it's broken the query down into the original subqueries, retrieved the chunks. Now it's calling the model on each chunk to work out, like, is it actually relevant? So you can see that 2 of the chunks it's going to discard. Okay. This might take a little while. So how are people going, by the way? Any questions so far? Yeah, of course, yeah. So the question is, when do you choose to have, like, your data ingested in advance, like we've done here? And when may you actually use, like, web search as a tool? Yeah, so I mean, I think it's sort of, okay. What we've done here is we've, like, amortized the cost of scraping the whole Zilliz website and putting that into a vector database. I don't know if I want everyone here simultaneously scraping the the Zilliz website. Might not be the best. So I think, like, the answer is, like, a combination is ideal. So to build, like, a more sort of, like, I guess, like, sort of the version on top of this, we might add, like, web search as a tool. And it might say, so we might give that the agent the option to say, okay, I'm actually going to perform a web search now. But, you know, something like an internal application, it's, you know, your website's probably changing much less often than, like, the web as a whole. Yeah, so exactly. So yeah, those are 2 good examples. So internal websites and other things, maybe like images, sound, video, that are a bit more static. Okay, so while we were having that discussion, it's been reasoning away and reflecting. So it went through the first iteration, and then it decided, okay, there's actually a few gaps in my knowledge. So I'm going to ask these 3 questions, go through that again, filter the chunks, and then after the second iteration, it says, that's enough. Like, there's no gaps in my knowledge, so I'm going to terminate the reasoning loop. So now we can just go ahead and generate the report. And the report will take all of that information over these loops of the agent. So we'll put in the original query, we'll put on all of the unique subqueries over all of those loops, as well as all of the unique chunks that it fetched. And then, so we'll run that prompt. And this should be fairly quick. So for anyone here who has an open API key, have you been able to run the model? Have you been able to get up to this point? Yep, awesome. Okay, so this one was a bit longer because it had to generate a lot more tokens just by the nature of the query. It had to input a lot more tokens too. So let's output the response. Okay, so this is what it's output. I've just copy and pasted, like, a previous output into the next cell, and because it's Markdown, it will be able to visualize this in the Visual Studio Code editor, or Google Colab if you're in there. Okay, so let's take a look at this. So, you know, it starts off with introduction. So it looks like it's sort of like giving this a nice structure, overview of Milvus, key features, then going into a bit more detail. So comparing it to other vector databases. So, you know, it seems like it's doing a reasonable job of writing a report. It's sort of looked into, like, the sort of like the sub-questions that we need to fully answer the overall question, and then synthesize that into, like, a logical structure. So, you know, you might be, like, curious to try it out with your own queries. Does anyone have any suggestions? We could do one live. Okay, maybe for time purposes we won't. So that's it for the notebook. So hopefully you learned something. This is just like a really simple example of how you can use a reasoning agent to construct like a research agent that can do useful things and write reasonable sounding reports. If you were to build on top of this, you might want to add in other types of tool usage. Definitely being able to do web search would really increase the power of this code. So yeah, that's it for the code part. Let's go back across to. Okay. So we built a simple agent. I just wanted to reflect a bit on what some of the challenges are of research agents. So firstly, I think there's sort of like three big challenges. Firstly, just like getting the data to actually train your reasoning models if you're not using a closed source one, or I think we're going to see more and more really, really high quality open source reasoning models. The second one is the cost. This reasoning agent had to do a lot of calls, a lot of inference, and so that's going to sort of, that's why it sort of might take 10 minutes, half an hour to go off and research this report for you. So there's like a cost aspect there. And then there's just like sort of like scaling, other aspects of scaling that are not related to cost. So more on like the hardware infrastructure side. And I think that's where Zilliz can really come in and help. So we talked about Milvus. So that's like the open source version that is self-managed. But we also offer a fully managed service, Zilliz Cloud, as well as a bring your own cloud version, Zilliz BYOC. You might really want to sort of have a large vector database, but you don't want to do, you don't want to sort of like incur the hassle and the cost of managing it yourself. And so that's where a fully managed service is really helpful. I've added a little link here to the sign up for Zilliz Cloud. We have like a free tier offer, which is actually one of the like easiest ways to start working with a Milvus database. So you can click on that link and set up an account. But with that, I wanted to wrap up and say thanks everyone for coming.